Welcome back. We're now on 9.5, the kinetic molecular theory. In this, we are going to state the postulates of the kinetic molecular theory and use this theory's postulates to explain the gas laws. So, kinetic molecular theory, otherwise known as KMT, because chemists are lazy. It is a microscopic model that effectively explains the gas laws we've explored so far. So we have 5 main parts of KMT. The first is that gases are composed of molecules that are in continuous motion, traveling in straight lines, and changing direction only when they collide with other molecules or with the walls of a container. So they just go on one straight line until they hit something, and then they bounce off and go in another straight line, and that's how the gases are moving. The second, the molecules composing the gas are negligibly small compared to the distances between them. So the molecules or particles of the gases themselves are super, super tiny, and the space between them is massive. So much so that the size of the actual molecules is practically negligible. The third, the pressure exerted by a gas in a container results from collisions between the gas molecules and the container walls. So pressure is related to the number of times that the gases are hitting the walls of a container. 4. Gas molecules exert no attractive or repulsive forces on each other or the container walls. Therefore, their collisions are elastic, meaning they don't involve a loss of energy. So if 2 gas molecules hit each other, they just bounce off, go in other directions with the same amount of energy they had to begin with. They're completely elastic, just bouncing off, keeping the same energy and doing their thing. And the last one is the average kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. So this is what makes up KMT, and we're going to go through very quickly the other gas laws and how we can use KMT to describe them. So starting with Amonton's law, if the temperature increases, the average speed or kinetic energy increases. Little typo there. So volume is remaining constant here. Okay, so with the volume staying constant, increasing the speed, that should be a D, the increased speed causes there to be more collisions. So the gases are hitting the walls of the container and each other more often and harder. And so because of that, now we're increasing the pressure. More collisions, more pressure. Okay, so we increase the temperature, they're moving faster, which means now that they're moving faster, they're going to hit the walls of the container more often, which now gives that higher pressure. Now, Charles's law, we're increasing our temperature, and the volume has to increase to maintain constant pressure. So what's happening is if the pressure were to stay, if the volume didn't increase, the pressure would go up because of increased collisions. So the volume has to increase with that increased temperature so that the particles now have a longer distance to travel to hit the walls of the container. And so there's also now more surface area from the container, so there's less collisions overall. So this is going to balance that increase in kinetic energy that the particles now have and keep that constant pressure. Boyle's law, we're decreasing our volume, so the area of the walls are decreasing. So now the number of collisions are going to increase because now there's less space for the gases. So now they're hitting the walls of the container more often, increasing the pressure. The next is Avogadro's law. And so the frequency and force of our wall collisions are going to be constant at constant pressure and temperature. So if we add more molecules, then we need extra volume, because if we add more molecules, we're going to have more frequent collisions with the sides of the container. So we need more volume to end up keeping everything else constant. And then lastly, Dalton's law. Molecules of one gas are hitting the container walls with the same frequency. It doesn't matter if there are other gases present because there's all that extra space in between the gases. So the total pressure is still going to equal the sum of all the partial pressure. So here's just some pictures showing this. A for Montan's law, increasing the temperature and keeping volume constant is going to increase the pressure because now these molecules are moving faster. B is looking at Boyle's law. We're decreasing the volume, so now there's less wall area. So that means these particles are going to be hitting the sides more often, increasing pressure. And then C is looking at Avogadro's law. With the pressure being constant in the container, we have more gases being added, more molecules, so we have to increase the volume to account for this even pressure and increased molecules. All right, so let's talk about molecular velocities and kinetic energy. So there's a lot of molecules and collisions going on. So there's actually a distribution of the speed of these molecules, and it might look like something like this. And this is called the Maxwell-Boltzmann distribution. So this is usually your velocity or your speed on your x-axis, and your y-axis is your number of molecules. Okay, so you've got some that are going slower than others that are going faster, but you have this overall distribution happening. So each particle has some mass of m and some speed that we abbreviate with a u. And each particle has a kinetic energy that is equal to 1/2 the mass times the speed squared. For my physics people, this is basically kinetic energy equals 1/2 mv squared of anything. So you want your mass, though, in units of kilograms. Because when you do that and you have your speed as meters per second, then you get a kilogram times meters squared per second squared, and that gets you energy in joules. So that's how you get kinetic energy in joules. So we also have what is called the root mean square velocity of a particle, or U sub RMS, and it is the square root of the average of the squares of the velocities, where n equals the number of particles. So each particle has its own velocity or speed. So we take each one and square its speed, add every single one up, divide it by the number of particles, and take the square root of that. So now using this and substituting in this URMS into our kinetic energy equation, we can say that the kinetic energy is equal to 1/2 mu squared RMS, where if we can use m as the molar mass. And this is also equal to 3/2 times the universal gas constant times temperature. Now here for the R, instead of using the 0.8, I forget the full one that we used earlier, this is still a universal gas constant, but we're using different units. This one we're using 8.314 joules per mole Kelvin. So we can also say that RMS is equal to the square root of 3RT over m, where m is the molar mass. So this is just to give you an idea of the Boltzmann distribution and what these different U's are. So for instance, this is oxygen gas at 300 Kelvin, and we see there's all these different speeds, and so there's all these different particles that have these different speeds. And towards the tails of the distribution, there's a low number of molecules that have these speeds. But then you have your maximum, which is your most probable speed, which is actually a little less than the root mean square. And that's because this distribution isn't perfectly symmetrical, is it? It has this tail off part. So it has this extra on the side, which is going to shift the overall average, the root mean square, over a little bit. So, quick example, let's calculate the root mean square velocity for a nitrogen molecule at 30 degrees Celsius. First things first, turn that Celsius into Kelvin, add 273 to it. So we have a temperature of 303 Kelvin. The next is to get our molar mass of nitrogen in kilograms. So remember, this is nitrogen gas, which means it is N2. So its molar mass is equal to 2 times 14, so 28 grams per mole. But we need kilograms. So we know there's 1 kilogram per 1,000 grams. So its molar mass is thus 0.028 kilograms per mole. So we're going to substitute that into the URMS equation that we just looked at, 3RT over M. And when we look at our units, we see moles cancel from the R. We see the kelvins cancel up top. And we're left with joules over kilograms, which remember, a joule is a kilogram meter squared per second squared. So that divided by a kilogram has those guys cancel out. So then we get the square root of 2.70 times 10 to the 5th meter squared per second squared. So when we take the square root of that, boom, that square on each of the meter and the second cancel out, and we get 519 meters per second. So that is the root mean square velocity for a nitrogen molecule. So now we're going to talk about molecular velocity and kinetic energy. When we increase temperature, we're increasing kinetic energy. They are directly related to each other. Temperature is a way of understanding the kinetic energy of a system. So kinetic energy increases with this temperature increase. We're shifting our distribution of our speeds to the right, to higher speeds. If we decrease our temperature, we're shifting to the left. But all gases have the same average kinetic energy for their molecules at a given temperature. KE average, not the same kinetic energy, but the average of all of them. So here's an example looking at the speed distribution for nitrogen gas. As we go to these higher temperatures, it's shifting to the right and it's flattening also. And then as we have these lower temperatures, we're shifting to the left and getting this higher peak as well. We can also look at the molecular velocity compared to molecular mass. So this is all at one temperature for the noble gases, and we see the lighter molecules are going to move faster on average than the heavier molecules. So helium, being the lightest, has this wider distribution, but overall those particles are moving heavier than the others. So the last is looking at how KMT explains the behavior of gases, part 2. The average distance between molecules of a gas is really, really, really big compared to the size of the actual gas particles. So the gases can really move past each other super easy, and they can diffuse at pretty fast rates. But the rate of effusion is going to depend on the average speed of the molecules. So the effusion rate is directly proportional to the RMS speed. So we know URMS is equal to the square root of 3RT over molar mass. Rearranging everything for the molar mass, it is equal to 3RT over U squared RMS, or that average U squared. And we also know that the effusion rate of A divided by the effusion rate of B is going to actually be equal to URMS of A divided by the URMS of B. And then putting in the URMS equations, we get 3RT over MA, or square root of that, divided by the square root of 3RT over MB. Those 3RTs are going to cancel out. So then that simplifies down to the square root of the molecular mass of B divided by the molecular mass of A. So we just re-derived Graham's law. The ratio of the rates of effusion are inversely proportional to the ratio of the square roots of the masses. So this has been confirmed experimentally, and we have just seen it as Graham's law as well. We just went and re-derived it.